Hello, physics students. Today I want to apply what we've learned about free fall motion to a simple projectile problem. Here I have caveman Oog hunting a mammoth to feed his tribe, and we are going to calculate how fast Oog needs to throw a spear in order to hit that mammoth. Now, let's apply the 8-step plan. So let's read this problem carefully with active reading and circle the necessary information. So how fast does caveman Oog have to throw a spear horizontally? That's a key piece of information, so let's note that he's throwing it horizontally. To hit a stationary mammoth standing 120 meters from the base of the cliff, so 120 meters from the base of the cliff, if the cliff is 75 meters tall. All right, so let's take a moment and translate some of that information to this sketch. Now, I already have the sketch going on here. I have caveman Oog, and I have the woolly mammoth. Now, caveman Oog is going to throw the sphere horizontally. That is, my initial velocity of the sphere is here, and it is in the x direction. Okay. Now, it's very important to note that the spear is not going to go direct to the mammoth. The spear is going to eke out a parabolic path. The motion of the spear is going to trace out this parabola. Now, as the spear travels, the direction of the velocity is always tangent to the path. It's going to be getting larger as the spear travels. In fact, let me clean that up a little bit. So the velocity v is always actually tangent to the path. But we're not going to deal with the entire velocity v because we saw initially in the first video on free fall that we can treat the horizontal and vertical motion independently. So over here we can translate this motion. So the mammoth is standing 120 meters from the cliff. That is equal to an x value, but the cliff is 75 meters tall. That would be a y value. Now, again, I'm going to place my origin here at the start of the problem. And that means that my initial position x is 0 meters, and my initial position in the y direction is also 0 meters. The fact that the woolly mammoth is standing 120 meters from the base of the cliff, that is specifying an x value. And I need to be a little careful with the y value here. Oops, sorry about that. Now, if I place my origin with the where Oog is, this y value is below the origin, so I need to make a note that this is going to be minus 75 meters. Now, you'll see that if you make this mistake later on, you'll end up with trying to take the square root of a negative number, which is very common when you first start doing these physics problems. So just don't panic. If you end up in a situation where you're taking the square root of a negative number, it just means that you've lost a negative sign somewhere and you can just go find it. So the next thing is we want to make a table of our motion variables, but we want to do it in both the horizontal or x direction as well as the vertical or y direction. So let's take a look. Let's make a table of values. I'm going to switch to blue to make black to make it a little bit easier to see. Now, as we noted in this problem, the distance that the spear needs to travel in the x direction is 120 meters. the distance the sphere needs to travel in the y direction is equal to minus 75 meters. Because we place the origin at OOG, the initial position of the sphere is 0 meters. And in the y direction, the initial position is also 0 meters. Now, the initial velocity in the x direction, I do not know. Now, because I'm making a separate table of x and the y, this is why the AP puts x's as subscripts on their equations, or y's. So in theory, in actuality, this is the initial velocity in the x direction, and this is a question mark. This is what I'm trying to find. But the initial velocity in the y direction is not a question mark. This is a key piece of hidden information. Because OOG is throwing the sphere horizontally, I know that this sphere starts out with no horizontal velocity. I'm sorry, no vertical velocity. That is, the initial velocity in the y direction is equal to 0 meters per second. Now, that is not true as the sphere continues on. As the sphere continues on its motion, it's going to pick up velocity in the y direction due to gravity. But the x velocity will never change. That is, once I know the initial velocity in the x direction, it will stay constant throughout the entire motion because gravity only affects the vertical, or the y direction. Now, there are other key pieces of information here. Oops, let's go back. I know that the final velocity in the x direction, it's unknown, but it has to be equal to the initial velocity in the x direction because gravity doesn't affect it. The final velocity in the y direction is unknown, so that is a question mark. The acceleration in the x direction is going to be equal to 0 meters per second squared because gravity only acts in the y direction. So AY is going to be equal to gravity, which is going to be equal to minus 9.81 meters per second squared, and always points down. And the time is the same on both for in the x and the y direction. So sometimes I like to put the time down here to remind me that it's both for x and y. Now, signs are very important because every quantity in this problem other than the time is a vector. So the sphere is going in the positive x 120 meters, but down from the origin minus 75. So signs matter very much for these variables. All right, so I have these variables. So let's now find out how fast the sphere needs to be thrown. Now I'm going to cheat a little bit here. I'm going to highlight my variable table. And I'm going to make a copy so I can use it on the next page. All right, so again, we can use our motion equations from the AP constant sheet. I'm trying to... All right, here's the equations, and they're equally valid in both the x and y direction. I would just need to change my subscripts from x to y. So I am looking for the velocity, the initial velocity in the x direction. Well, there's a couple of different I can use here. If I take a look at the simplest equation, the Vx equals V naught x. Well, V naught x is what I want, but I know that Vx is the same. So if I go to that equation initially, so I also like to make a note that I'm working in the x direction here. So let me write that remind me that I'm working in the x direction. So I could say that Vx is equal to V naught x plus the acceleration times time. But if I put in that the acceleration is 0, that simply gives me the equation that the final velocity in the x direction is the initial velocity in the x direction, which I already knew, so that's not particularly useful. So I'm forced to go to the next equation. Now it looks all scary and quadratic, except for I note that the acceleration in the x direction is 0. So I can cross out that term, and because I place my origin at oog, I know that x naught is 0. So this equation simplifies that the position x is going to be equal to the initial velocity in the times time, and I can solve this equation for the initial velocity in the x direction. The initial velocity of the sphere in the x direction is going to simply be equal to the x distance divided by the time. Now I know the x distance, but I do not know time. That means math tells me if I have an equation with two unknowns, which I do here, the initial velocity in the horizontal direction x, as well as the time. If I have two unknowns, I need two equations. So fortunately, we have another dimension to the problem. We have the y equation here. Now, when you first start doing these projectile problems, it is often unclear which equation to start with, and should I start with the horizontal or the vertical. You develop a feel for the problems over time, but if I look here, I was looking for the initial velocity in the x, so that's what I started with. However, if I look over in the y direction, you can see that I kind of have more numbers to work with. I have both an acceleration as well as my y distances, as well as my initial velocity in y. So this might give you a tip-off that you would want to start in the y direction first, but there's no problem. I see here that I need time. I've already used my x information, so let me use the y information. So in the y direction, I do not have the final velocity in y. So I cannot use any equation that has the final velocity in it. That eliminates this first equation and the second equation. So I have to use the first equation, the third equation rather. So I have to use the second equation. But instead of x's, let me rewrite this in terms of y variables, since I'm dealing with the vertical. So the final position in y will be equal to the initial position in y, plus the initial velocity in the y direction times time, plus 1/2 acceleration in the y direction times time squared. So again, canceling out things that are 0, I know that y naught is 0. I know that the initial velocity in y is 0, which takes out this entire term. So this equation simplifies to y equals 1/2 the acceleration in the y direction times squared. All right, well, now I know what y is. I know what the acceleration in the y direction is, so I can solve for time. So I'm going to multiply 2 across. So I have 2 times y equals the acceleration in the y direction times time squared. I'm going to divide by the acceleration, and that will give me that time squared equals 2y divided by ay. And I'm going to get rid of the square by taking the square root. So that tells me that t equals the square root of 2 times y divided by the acceleration y. Now I'm going to put in my numbers. That means that t equals the square root of 2 times minus 75 meters divided by minus 9.81. Now, if you lost a negative sign, this is where you would notice that you were trying to take the square root of a negative number. Here, the negative signs cancel out. Again, if you end up in that situation, you don't panic. You just realize that you lost a negative sign, go back and find it, and put it into your equation. But now I will take out my tool of Satan to find out what this is. So 2 times 75 gives me 150. I'm dividing that by 9.81. And then I'm going to take the square root of that answer. And I get that this time works out to be 3.91 seconds. Now I can put that time into my equation that I found out below, and I can find out what that initial velocity in the x direction has to be. So the initial velocity in the x direction, which is x divided by the time, well, that's going to be equal to 120 meters divided by 3.91 seconds. And I see that the initial velocity in the x direction for the sphere will be 120 divided by 3.91, or that Oog needs to throw his sphere at 30.7 meters per second horizontally in order to hit that woolly mammoth. So there you go. So this is our first projectile motion problem. Now let's talk about if the sphere was being thrown at an angle. If, as an aside, if that sphere was being thrown at an angle, that is, if my initial velocity was like this, what would I do? Well, I don't know how to do a problem like that, but I do know that if I how to deal with velocity, with motion in the x and y direction independently. So if they gave me this angle here, let's say that this was so many degrees. Let's, as an example, say that this was 50 degrees. Well, what I would do is I would split this velocity up into a velocity in the x direction as well as a velocity in the y direction. And I note that I could complete my triangle here. And I can use trig. That is, I can use the fact, so if I was trying to find this initial velocity, what I would need to do would be find this velocity in the x direction and the velocity in the y direction independently. And then I could use trig to put it back together. And we'll see problems like that. But this is our first projectile problem. I hope it was helpful. And I will see you in a later video.